let's look at kinematics in 2 dimensions. We will start again by defining terms of quantities that we're going to be using. So the first thing is position, and it's no longer just an x or a y like we had in 1 dimension, but it's an ordered pair of coordinates. So we have an x and a y, x naught, y naught, which also stand for initial, x final, y final, whatever point in time you want to pinpoint a position. You can have an x1, y1, but there's always an ordered pair of x and y. Then we have the displacement, and we no longer write it as delta x or delta y. We're going to use a different letter, and in my case I just use delta r, where it is assumed that this r has an x component and a y component. So there's an rx and an ry associated with it, and this delta r is r final minus r initial, both vectors. So there is an x component and a y component to each of the r initial and the r finals. And now the displacement is more complex. It has both x and y directions associated with it. The displacement is measured in meters, and the symbol for that is just the letter m. The next thing that we're defining is the velocity, and first we'll look at the average velocity. And average velocity is just the delta r over delta t, so it's the displacement with respect to time. But if we want to look at the instantaneous velocity, then we have to take the limit as the delta t approaches 0 of delta r over delta t, and that is actually the definition of derivative. So the instantaneous velocity is a derivative of r displacement with respect to time. Both average and instantaneous velocities are measured in meters per second, and the symbol for that is just m over s. Average acceleration is delta v over delta t, and of course acceleration now can have an x component and a y component, so that's delta v x plus vy over delta t. So we have to keep in mind that these vectors all have x and y components. Then the instantaneous acceleration is the limit as delta t approaches 0 of delta v over delta t, which again is the definition of derivative. So the instantaneous acceleration is the derivative of velocity with respect to time, and it is measured in meters per second squared with the symbol m over s squared. So now that we defined our terms, let's look at the kinematic equations in 2 dimensions. And instead of just writing them as vectors, we like to simplify things. So we simplify things by working separately with the x direction components and then separately with the y components, and we combine them at the end to find whatever it is that we're looking for in a particular problem. So in the x direction then, we have the same kinematic equations that we've seen before, but we have to make sure to put the x subscript. So this is v final x equals v initial x plus acceleration in the x direction times time. Then final position x is initial position x naught plus initial velocity in the x direction v naught times time plus 1/2 times the acceleration in the x direction times t squared. And the last equation is final velocity in the x direction squared is initial velocity in the x direction squared plus 2 times the acceleration in the x direction times the displacement in the x direction. We do the same thing in the y direction. So we have the same equations, but now I substituted all of the x subscripts with y subscripts. So now we have to only look at components in the y direction when we write the kinematic equations in the y directions. So one application of this would be the projectile motion. So we're going to look at projectile motion next. Here we have the equation as I recopied them here, and then the projectile motion has a parabolic path like this. So for any object to take this path, something has to give it a velocity in this direction. If I just push something along the floor, it would go in a straight line this way. But since this object is going on a parabolic path, it means that it has a component to the velocity in the x direction and it has a component in the y direction. So I will first draw my initial velocity on here. So this is, I'll call it V naught because I've been using V naught as my initial velocity. And I know that that V naught will have an x component, so I'm going to draw a projection onto the x-axis, and here is my x component, so I'll call this V naught x. And it also has a projection onto the y-axis, and I'm going to call this V naught y. And we're going to follow all of these vectors only in the x direction or only in the y direction. So I'm going to draw here my coordinate system. Here is my y going straight up, and here is my x going to the right. And we're talking about projectile motion on Earth, something that we are able to observe. So let's say that there's a ball that's being kicked, and that's what this path is. It's a ball starting here and is kicked and it lands over there. One thing that we have to assume is that there is no air resistance, there's no drag, so that our motion is going to be very simple, just a parabolic path like that. So we know that the reason the ball takes this path rather than just shooting straight up and keeping going is because gravity pulls down on it. So we have the acceleration of gravity that goes down like this, and we have the acceleration of gravity acting everywhere along this path. So the only direction that this acceleration acts is in the negative y direction. So I'm going to call this negative g, because I know that it's negative 9.8 meters per second squared on Earth. So the negative sign stands for the direction, and g is the magnitude, which is 9.8 meters per second squared. Now, I only have an acceleration in the y direction, and a result of that is that the velocity in the x direction does not get affected in any way by an acceleration, so that means that it will stay constant. So the acceleration in the velocity in the x direction will be constant throughout the motion. So I'm going to draw this V naught x here, and I can say that everywhere along this motion I have velocity in the x direction V naught x. It doesn't change because there's no acceleration acting on it. But what happens to the velocity in the y direction, the component in the y direction, is that since gravity pulls down on it, it keeps decreasing. It gets smaller and smaller until it's zero at the top, and then it starts falling back down. So it's going to increase more and more until when it reaches the bottom, it has a V final in the y direction, down like that. Now, since there is no air resistance, or we assume that there is no air resistance, the motion is symmetrical. So this initial velocity in the y direction has the same magnitude with the velocity in the y direction at the very end. If I were to draw a horizontal line over here, then I would know that this velocity in the y direction has the same magnitude as that velocity in the y direction. So again, it's a symmetrical path. And if I draw a perpendicular here, then I know that everything on this side of that line is symmetrical with everything else on the other side, but in the y direction, things are acquiring a negative sign. It's a negative direction. So let's rewrite the equations, the projectile motion equations in the x direction, and see what we can come up with. So one thing we know is that in the x direction, there is no acceleration. So that means that I can cross this one out, I can cross that one out, and I cross this one out. So what am I left with? It looks like I have Vx equals V naught x. And that is what I already said over here, that the velocity in the x direction is the same as the initial velocity. So Vx anywhere along that path is the same as the initial velocity in the x direction. Then in the second equation, I have x equals x naught plus v naught x times t. And if we rearrange this, we basically get that v0x is x minus x naught divided by t, which is the definition of velocity, delta x over delta t. If we look at the third equation, again, we get no information from it because we have just vx squared equals v naught x squared since this term is 0. So it turns out that in the x direction, we have a single equation that's of any use to us, and that is the definition of average velocity. Now let's look at the y direction. So we know that in the y direction, the acceleration is negative g. So if I rewrite all my equations, then I have v sub y equals v naught y minus gt. Then y equals y naught plus v naught yt minus 1/2 gt squared. And vy squared is v initial y squared minus 2g delta y. Now, these are not equations to be memorized. You should be able to figure out these equations by just knowing that in the x direction, the acceleration is 0, and in the y direction, the acceleration is the acceleration of gravity, which is negative g. So now, once you figure out things in the x direction and then separately things in the y direction, you can combine them and solve for the vector velocity at the end of the path or at a certain time t, whatever it is that the problem is asking you to do. The thing that connects the x and y motion is the time. So we have the same amount of time necessary for an object to move in the x direction as it needs to move in the y direction, so that it would go from, let's say, this point to that point. The amount of time that it takes for it to go to the right in the x direction is the same amount of time it takes for it to go up in the y direction. So these times are going to be the same, and they connect the motion. And if I want the final velocity, then what I would want is just v final, which is the square root of vx squared plus vy squared, and I will want its direction, that is given by the inverse tangent of vy over vx. So I can always use these equations to combine the x and y motion, and I can always use the time to relate the x and y motions as well. So the next concept is that of relative velocities. So let's look at what exactly this means. We're talking about relative velocities when an object is observed in its motion from two different reference frames. So what we mean by that is, let's say that you are moving in a car, and with respect to that car, relative to that car, you have no velocity. You're moving at the same speed as the car. But if somebody is watching you from the sidewalk, from outside the car, they notice that not only the car is moving, but you're also moving. So in order to wrap our minds around this, we have to be very careful with how we write this out. So we're going to be using subscripts, and the subscripts are going to be somewhat like this. Let's say that we have the velocity of the person relative to the car, and we have the velocity of the car relative to the sidewalk. So by person, I meant the person riding in the car, and the sidewalk is the person in the on the sidewalk. And then we have the velocity of the person relative to the sidewalk. See how fast that person is moving. And to figure this out, there is a very nice trick. Here's the trick. If you have the velocity of object A relative to object B, that is equal to the velocity of object A relative to a third object C, plus velocity of object C relative to object B. So the first subscript is the first subscript in the sum. The second subscript is the last subscript in the sum. and then the middle subscript here drops out. So looking at my problem, velocity of the person relative to the sidewalk then will be velocity of, I have to start with P, of the person relative to the car, plus velocity, I have to start with a C now, so that's velocity of the car relative to the sidewalk. So that I start with P, I end with S, and the C drops out. So this is how we're going to be doing the relative velocities. Now this gets more complicated when things are not moving in just a straight line, where you have a velocity in this direction and a velocity in that direction. Adding those becomes more difficult, and we're going to see that in solved problems. We'll see how to reconcile this problem. So here is a summary of everything that we've discussed here. And the very last thing that I'm leaving you with is the equation for relative velocities. It's just a guide of how to double check that your subscripts work out when you're setting up a problem.